Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today is a very important day from many points of view, and I'll tell you why. Um, Firstly, we are just going to get started for the class 11 students with gravitation, right? We have spent many weeks discussing um, rotation, rolling, and finally also discussing angular momentum, torque, various ideas around that, right? So now we are going to introduce, a set of related topics, you know, which integrate the various ideas that you have learned so far. We started with calculus and vectors. Then you learned kinematics. Then you learned forces, right? Then you learned the dealings after forces energy, right? So then you finally learned about rotation and torque, right? So one, two, three, four, five. Now this is the maybe the sixth topic, but in fact, gravitation was what was the first subject that was discussed in mechanics. You know, there is this lecture given by um, Professor Feynman, you know, and he discusses how the world moved from its original what is called the Earth-centric theory, the heliocentric theory, and he discussed all the various ideas that came about, and then from there on, how things continued to change in mechanics all the way to special relativity. You know, now you will learn a little special relativity, particularly for the for the JEE students. But today we are going to discuss this amazing thing called gravitation. Okay? And when you learn modern physics, you will understand what is gravitation. Okay? As we all know, gravitation is a weak force, right? So before I go forward, right, let me first make it, And as you all know, we always start out with the picture of Sir Isaac Newton, right? Isaac Newton is true mechanics, right? He was the first person who codified everything, He had a role in calculus. He had a role in Newton's laws. He had a role in, defining, what was then mechanics, right? And but then before there was Newton, it was not like no one had known or any of this. Many people, maybe even ancient India, they suspected that the sun was at the center of everything, you know. And the heliocentric theory is commonly was commonly known in many places. There were many who, I think, even in the early days, I don't know, there was one person who assumed a heliocentric theory, and on the basis of that, found the radius of the Earth with some degree of error, but he was able to find that because he made that heliocentric assumption. Then he said the radius of the Earth is round, and this is its radius. And this is not someone from the modern era. You know, now this was a big debate, but before we discuss this debate, I am going to discuss our Independence Day special. Okay, our Independence Day special package is now available and is available for just a few days. We have reduced prices by 30%, taking into account our Independence Day, which is coming up the 15th of August. And we want this to be the Independence Day for all students so that they can come on board and start studying from using our app, our two apps, right? So if you are a NEET student, go to our go to Play Store and download Sushruta for NEET. And if you are a JEE student, you download Ramanujan for JEE from the Play Store. We are very interested and excited to have Sushruta for NEET and Ramanujan for JEE made available to students. But hurry up. This offer will expire and it will expire in 2 weeks before you know it. I am going to give it exactly 3 days after Independence Day so that you can take advantage of this offer. What was 89.95 is now 59.95. Okay? So you will get a full year service for 59.95, which is the lowest program you will get. Many places they charge 59.95 a month, So you are well off, much better off just getting the package for a whole year. Okay. So this is our Independence Day special. Tell your friends, download the app and get going. Okay. The strong equivalence principle suggests that the laws of gravitation are independent of velocity and location. The gravitational motion of a small test body depends only on its initial position in space and time, in space, time, and velocity, and not on its constitution. Okay? So this is a very simple principle, but it is a very essential principle. You are where you are, as they say, right? Similarly, everybody in the universe is where it is, right? The planets and the stars, they are almost compared to us ephemeral beings, they are almost eternal and were seen as eternal by the early humans, right? Now, when we look at this, equivalence principle, what it states is that a body's position, right, in space-time and its velocity, right, these two alone, the gravitational motion of a test body depends only on these two and not on what else is inside it, right? Just because you are sitting in a particular planet doesn't mean its behavior will change, right? There is nothing special about you or me or anyone else, right? So in the grand scheme of things, there are only these laws that operate at the macro level, and the law of gravitation is one. Okay. So now, having said that, gravity is what is called a weak force. It is not as strong as the other forces that we know. For instance, electromagnetics, and the even stronger force, which is the nuclear force, which is the force that binds the parts of the nucleus of an atom together, which is called the nuclear force. And so when you learn about these forces, understand that the four forces that are there are two that are weak and two that are strong, and gravitation is a weak force. Now, having said that, right, we will now go into the early days before there was Newton. Okay? Before there was Newton, there was first Galileo. Okay? Galileo, he did the following experiment. He put a, I think, glass tube, okay, and he made two glass tubes and created a vacuum. He pulled all the air out of these two glass tubes. And then from the top of the glass tube, he dropped a feather, and I think it was a coin, but something made out of metal. And when he dropped it, he found that in vacuum, both the feather and the coin reached the bottom at the same time. And this was the beginning of the discovery of gravitation. Galileo is most famous for his heliocentric theory. Okay, and the person who took Galileo's heliocentric theory and then went on to describe the three laws was Kepler. He had three laws. He did not come up with, he did not discover gravity, but he explained the motion of planets. But before there was Kepler, there was Tycho Brahe. Tycho Brahe was a very rich man based in Netherlands, and he, because of his wealth and his interest in these things, in planetary motion, he purchased a lot of telescopes and various items, and then he started studying them, you know, and then he looked at all the stars and the moving planets. Then he said these planets, they follow a particular uh, pattern, you know. And then he brought on board this guy Johannes Kepler. Now Kepler, after many years of effort using Tycho Brahe's equipment, came up with these three laws. Okay, the first the first law is codifies the heliocentric theory, which states that every planet moves around the sun in an elliptical orbit with the sun situated at one of its foci. It's that everything moves in an elliptical orbit with the sun at the center of the ellipse. The sun sat at one of the foci, and the planets revolved around it. Okay. Now, the second law was a more complicated one. Okay. What it stated was that it is called the law of aerial velocities. A planet moves around the sun in such a way that its aerial velocities are constant. And we looked at this law also in the last class, right? dA by dt is a constant. Now, the third law, and I explained how it relates to the idea of angular momentum, right? Angular momentum is conserved because, and you know why angular momentum is conserved. Although there is gravitational attraction between the planet and the Earth, right? Between the planet and the sun, right? Although there is gravitational attraction between the planet and the sun, right? The 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 fact that the planet and the sun, there is a conservation of angular momentum, you know, and because of that conservation of angular momentum, we end up with this idea that the aerial velocities are constant. And so what does that mean? The aerial velocities are constant. It means that mr square d theta by dt is a constant. So if mr square d theta by dt is a constant, then you have this dA by dt is a constant. Why is r square omega very important? R square omega is the aerial velocity. Okay. Half, if you look at a circle, right? You look at a circle, it, what is the area that is covered, right? The area that is covered is the circumference, which is r theta, right? The circumference covered when the planet goes through an angle theta is r times theta, right? Now, 2 pi r times theta times the r radius gives you the circumference, right? That is because you've gone a full circle, right? Similarly, r times theta gives you the arc that has been covered. As theta tends to be very small, r d theta gives you that that length covered, right? Now, if you say that it is almost a straight line, the arc covered is almost a straight line, and you make a triangle with the center, then you have half times r theta times r, half base times height. If you make it a triangle, right, will give you the area, right? So half r square theta gives you the half base times height is the area of triangle. So half r square theta gives you the area. Okay. So now, if you instead of this, if you then take the derivative of that dA by dt, then you have half r square d theta by dt, right? Now that will give you half r square omega, right? And dA by dt is a constant, right? dA by dt, half r square omega, is a constant, is the same as saying I omega is a constant. So, and I is merely mass times mr square times omega, okay? And therefore, I omega is merely mr square times omega, right? So, therefore, r square omega is a constant because the planet's mass does not change. Therefore, mr square omega is also a constant, right? So, I omega is a constant is another way of saying that the aerial velocity is also a constant. Okay, so that is Kepler's second law. Now, Kepler's third law, right, is that a planet, moves around the sun in such a way, right, that the square of its period is proportional to the cube of the semi-major axis of its elliptical orbit. Okay. Now, the third law, right, is a direct result of the more important and famous law that you do know, which is Newton's law of gravitation. Okay. Now, Newton's law of gravitation states that gmm by r square is equal to the force, right? The force of attraction between any two planets, and gmm by r square is represents the force, came later, right? The force of attraction between any two bodies in the universe. For a man to come up with such an with such a grand solution is why people praise Newton so much, right? The force of attraction between any two bodies in the universe is proportional to the product of the masses and inversely proportional to the square of the distance between them, right? So now, if you look at the why there is conservation of angular momentum in Kepler's second law, it is also a consequence of this gravitational force. Okay, it is because there is only this one force, right, between the sun and the planet, right, and that is the main force that we are looking to observe. It is because of just this one force that there is no torque, right? The force is in the same direction as the rotation, right? So the position vector, the r with respect to the revolution, right? The planet goes like this. At any point, the r is like this. The s is also like that. So r cross s is 0 because r and s are the same. So if you measure its rotation about this axis, r cross s is 0. Therefore, the I omega is constant. There is conservation of angular momentum because the force and the axis of rotation are the same. Okay? So r cross s is 0 because r and s are the same direction, and that is what decides also Newton's Kepler's second law, which is that I omega is a constant, or or r square omega is fixed, which is the same as saying that dA by dt is fixed, right? Now, the third law can be derived completely, more or less completely, not completely, more or less completely, if you assume that gmm by r square, and you say that gmm by r square equals m omega square r, right? Uniform circular motion. You use uniform circular motion, and you can derive it. I don't think one needs to too much figure out how to handle ellipses, but you could, if you use ellipses also, you will arrive at the same answer. Okay, so now we return to Kepler's second law. And so Kepler's third law is T square is proportional to R cube, where T is the period, the square of the period is proportional to the cube of the semi-major axis, or the radius, right? If it was going in a circle, it would be a radius. So T square is proportional to R cube, where R is the radius of the orbit, right? And semi-major axis is just is a more precise way of saying it's a radius. In a circle, the semi-major axis is the same as the radius, because there is only one, a circle is a special ellipse, right? So T square is proportional to R cube, right? So T square equals 4 pi squared by Gm times R cube, right? So we will discuss that a little later, but then you can very easily derive it. You just put gm by r square equals m omega square r, and omega equals 2 pi by t. You will end up with that formula. Okay. So now, what is important is when you look at Kepler's laws, right? When a planet is closest to the sun, right? At that moment, it will be covering the largest angle. Okay, the A that it will, the A at that point, the R is the smallest, but the angle has to be the greatest, so that the area stays the same. Okay, so when you look at these, not every planet has the same kind of ellipse. Okay, there are other bodies which revolve around the sun, which go very far away and then come very close. Okay, the most interesting of these are these bodies called comets, right? The comet, many comets, they have extremely elliptical orbits. Okay, so there is a point when they are closest to the sun, at which point they are moving at great speed. Then they go to a very far distance. At which point they completely slow down. Because the angle, right, the area at those distances, right, becomes less. Okay, so as a result, you find that r square d theta by dt, right, where r is the position vector, r square d theta by dt is a constant, and therefore that is the area covered is constant, which means that the angle has to proportionately rise based on the distance. Further, they are the greater the distance. The further they are, the longer the distance, and therefore the dA by the d theta by dt will correspondingly decrease. So r square is inversely proportional to d theta by dt. R square d theta by dt is a constant. Therefore, r square is, so d theta by dt, or which is the same as omega, right? D theta by dt is the angular velocity. Omega is proportional to 1 by r square. Or so keep that in mind. So the angle covered is the same, right? And the third law of Kepler is same as Newton's law of gravitation, T square is proportional to R cube. So it's a planet which is further away, right? What is going to be its period, right? So that you get from these results, right? So now you know so how did they find these things out? I don't know all the details as to how they found a law like this. T square divided by R cube is a constant, but definitely for someone, before discovering Newton's law of gravitation, to discover T square is proportional to R cube, it's definitely a great achievement. They must have had some way to measure distance, and between planets, and between the planet and the sun, you know. So they must have used a lot of trigonometry to discover it, and then used maybe details around what is that, eclipses, right? To find out. So if it eclipsed at this point, then it will eclipse again at this point in time based on the periods. They would have tracked the periods of at least some of the planets closer to the sun, and then of course they know the Earth's period, etc. Right? And so on the basis of all that, they were able to find of eclipses happening, and these planets. They were then able to find the T square is proportional to R cube. So now, having discussed this, what is the value to you, right? The value to you is to solve problems, right? So the period of a satellite, and to be able to analyze these things pretty quickly and easily. The period of a satellite in a circular orbit of radius r is t. The period of another satellite in a circular orbit of radius 4r is, okay? So t square is proportional. This is just the direct application. T square is proportional to r cube. So if you wanted to start from scratch and derive t square is proportional to r cube, be my guest. But if you see something like this, you immediately recognize circular orbit, t square is proportional to r cube. Therefore, now if for this, if t square by r cube equals a constant, then for the other planet, it is T2 square by 4r the whole cube is what? 4r the whole cube is 64, right? So, so now you divide the two equations, you find that Ta square equals T square times 64, right? Therefore, because the r cube will cancel, the 4 cube is 64. Therefore, Ta square equals 64 times t. 64 times t square. Therefore, Ta equals 8t. Right? Therefore, you end up with the period of the other satellite is 8 times the period of the first. Right? So very straightforward question. T square is proportional to r cube. Just divide it. Right? So a planet moves around the sun at a given point P. It is closest from the sun at a distance d1, has a speed v1. Another point Q, when it's furthest from the sun, its speed will be, right? So now half r square d theta equals dA. So dA by dt equals half r square d theta by dt, right? So r d theta by dt is v, right? R omega, v equals r omega. So r v equals k equals a constant. So r1 v1 equals r2 v2, or d1 v1 equals d2 v2, right? So we thus have d1 v1 equals d2 v2, right? So and if you write d1 v1 equals d2 v2, so d1 v1 by d2 equals v2, right? So at what is, when it's farthest from its speed will be d1 v1 by d2, right? So this is merely a second law problem. Now, when do you apply first law? When do you apply second law? When do you apply third law? That's what That's why you need to learn, the ideas behind these, these questions. That's why we teach it also in that order, right? Kepler's second law regarding constancy of radial velocity of a planet is the consequence. The law of conservation of angular momentum. Move on, right? So now we will discuss, we will now introduce the ideas around gravitational potential energy, right? When we have the small matter of some things known as satellite, and these days, of course, there is also this great craze or clamor around space travel, right? There are people, Jeff Bezos, Elon Musk, Richard Branson, who are all saying we all want to go to space. We'll take you also. Just write me a check for 500,000, right? You have $500,000. I will take you to space and bring you back safely, right? So now, those of us who don't have $500,000, there is, of course, does not mean that we cannot take an interest in matters dealing with space. We can learn all the physics and the maths and look at, buy a telescope and watch the planets in the evening, right? And when it's an eclipse, we see it. When it's a beautiful moon, we can still enjoy a great moonlit dinner, right? So wonderful moonlit dinner, nothing beats it on a nice evening, right? It is even better. Believe me, it will be even better than going to space. Now, what is gravitational potential energy? Gravitational potential energy, as you know, is mgh. Now, if I have this, let's say it's any body, right? Now I lift it by a distance h, m times g times h is the gravitational potential that I've added, right? So now, how do you look at this gravitational potential energy in the context of a body which is in far away, right? That gravitational potential energy is, you have to understand this idea very clearly. Only then you will be able to solve some of the problems and also understand this material, right? A conservative force is a force of the form F of R, right? Now where everything else is constant, right? So now GMM by R square is of that form F of R. It is of the form, I'm more accurately speaking, 1 by R square, right? So GMM by R square is the force, right? The force is when you have a force in this, when you have a force like that, right? Then the the work done to move it from one place to another in that what you call field. Okay, so now we say that all the planets exist in the sun's field, right? And you will learn more about field when you look at also at the electrical force, which is also an inverse square law, right? So now what you then do is you write that force as the gradient d, so du, or gradient of the potential. Okay, so now define a u, okay, and you write it that du by dr equals, okay. Now the term gradient, you will learn about it a little more when you go and learn vector calculus, right? Gradient takes a scalar field and produces a vector. Okay, so it is a directional derivative. So it is called, shown with an inverted triangle called grad. So it's called grad phi. Okay, so if you define some phi as a potential, right? The potential function. So it's a function of x, y, and z, right? So f phi is equal to f of x, y, and z. It's a scalar, but it's a varying scalar. You take the gradient, you will end up with a vector. So grad of the potential will give you the force. Okay. So du by dr is the force, and if you therefore integrate from force, you will end up with the gravitational potential. Okay. So F dot dr, you know, is the work. U is related to the work. You already know that work energy theorem, right? So du by dr is the force gradient of the potential, right? So now, so if I gave you gmm by r square and you integrate gmm by r square dot dr, right, you will end up with minus gmm by r. Okay. Now, why I teach you these details is, let's say they told you it is r cubed, right? Then you have to redo the calculus, right? But if it is not r cubed, standard gmm by r square, then you end up with minus gm1 m2 by r as the gravitational potential energy at a distance r, right? So now, in a conservative field, it is only the endpoints that matter when it comes to looking at work, right? There is, when a body goes in uniform circular motion, there is no force. The centripetal force doesn't do any work, right? Because the direction of travel and the direction of the force are perpendicular. So F dot V is 0, right? So anything that in that orbital just keeps going round and round and round and round forever in the context of that one force, right? There is no work done, and it just keeps going round and round and round forever, right? So now, if you want to move it to another um, orbital, right, then you have to do work. Someone else has to come and do work in the context of this gravitational potential field, right? So we are all living in stuck in this, in the field of the Earth, right? And so who is going to do this work? Why do they charge 500,000? It is to do that work, to ship you all the way to the sky, right? So if it was, if you assumed that, see this gmm by r square, right? Normally you say that it is a just mg, right? Little g is gm by r square. R is the radius of the Earth. So near the Earth, we say, the r doesn't vary much. So between this point and this point, we say that actually the distance between this and the center of the Earth does not change much. Okay, we are saying we keep it a constant, right? So for small distance, because what is the radius of the Earth? It is several thousand kilometers. I think 7, 8,000, 6,000, 7,000 kilometers. That is the radius of the Earth, right? The circumference is something like 40,000 kilometers. So the 6 times the radius, right? 2 pi is how much? 6.3 almost, right? So now gmm by r gives you the gravitational potential energy, right? So and if you need to, so we'll do a few problems dealing with this idea of the gravitational potential. Now, force of attraction, we need to mass is gm1 m2 by r square, and that leads to Kepler's third law. We already said t square is equal to r cube can be derived from gm by r square equals m omega square r, right? So therefore you have t square is equal to r cube from that equation, right? So now what we are assuming is now the other question is, if you assume that the Earth is a uniform sphere, and then you bore a hole through the Earth, what happens to G? Right? Well, actually, the Earth is not that uniform a sphere, right? At the center, there's a lot of molten lava, or molten material inside. That's what comes out when you dig it, and or when there's a volcano, you see so much molten lava, right? Now but if you assume that it was a uniform sphere, right? You can then say that you can then model it. You know, a lot of things are just modeling, you know. So its mass is rho times dv, right? Now, if you go some distance into the Earth, right, you take only the Earth that is in front of you, right? The Earth that you have crossed, that part of the Earth doesn't produce a gravitational field. You won't believe me, but that's how it is, right? So if there was a hollow sphere, right, and you went inside that hollow sphere with a uniform mass density, right, inside, or you had a huge hollow sphere and you went to the center of that hollow sphere, you know, inside there will not be gravity. That's a very counterintuitive idea, okay? And therefore, when you look at gravity, right, as you go inside the Earth, it will start to become, the gravitation will keep decreasing as you go inside the Earth, just as it keeps increasing as you go above the Earth, right? So as you go further and further above, like as you go near the moon has a very different, faces a very different gravity from the Earth compared to what we face. We end up with the greatest gravity because we sit right on the surface of the Earth. Okay? So inside it's a linear line, outside it is a inverse square law. Okay? So anyway, so let's look at this problem. So it looks like this, then like that. Okay, so at the center of the Earth, 0. Okay, the elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest and nearest points to the Sun, right? At position 1, the distance from the comet to the Sun is 10 times the distance at 2. At position 2, the comet's kinetic energy is, okay, so at position 2, what is the comet's kinetic energy, right? So, well, the comet is the same as at position 1, right? So, you should remember this one, this question, right? dv equals constant, right? So, if you remember that, you can easily look at this. Otherwise, you just start with gmm by r square equal mv square by r, and then you try to make a relationship, right? So, but dv is a constant will tell you that at position 2, right, the d is the smallest, so the v is the largest, right? So at position 2, the comet's velocity is the largest, right? And because the comet's velocity is the largest, half mv square is the greatest. Okay, so the comet's kinetic energy is at its maximum value for the orbit, right? So now, what is the ratio v1 by v2 of the speed of the comet at position 1 to the speed at position 2, right? So dv is a constant, means that if d1 by d2, right, is 10, then v1 by v2 will be 1 by 10. dv is a constant, means d1 by d2 equals v2 by v1, right? So if d1 by d2 equals 10, v1 by v2 equals 1 by 10. Very straightforward, right? So now, what is the ratio F1 to F2 of the force on the comet at position 1 to position 2? That is very straightforward. GMM by R square equals constant. M's are same. G is a universal constant, 8.85 10 to the power minus whatever it is, or whatever, not 8.85. Whatever that value is, you should learn what that value is. It is some very big value. G mm by G is universal gravitational constant. It is not little g. Little g is gm by capital R square, right? So capital G is a constant for everything, regardless, it's a fixed constant for the world, right? For the universe, right? So gmm by R square. So what is the ratio of the force F1 to F2, right? Forces are different. Forces are different. Forces are proportional to the square of the distance, right? So at 1, right, the distance is 10 times. So 1 by 100 times the force when it's at 2, right? So gravity changes, as you all know. It goes highest at the Earth's surface, and declines as you go into the sky, right? And it declines as you go into the Earth as well. But so that is the next slide that we come up with. The actual variation looks something like this, but the theoretical variation is just a straight line. G naught is this point. This is G naught. Okay. Now G equals G naught minus H G naught over R. Okay. So that is just the straight line, right? So if H equals R, G will be 0, right? So G is this portion of the line. Okay. Now this portion of the line is merely the inverse square law, right? So at the Earth, this is at the radius R, capital R, right? So at a distance little r, right, it is going to be G naught R squared by little r squared. Okay, so it is going to be less, and it's a inverse square law, right? What is 1 by r square, right? If something is y equals 1 by r square, it is going to look something like this, right? Y equals 1 by r square. Okay. Okay. So now at these points between here and here, right? Although it should be a inverse square law, sometimes those points, because it's closed, they model it as also linear. Okay, and that linearity is not given by 2g naught by capital R. Okay, rather than g naught by R. Okay, or try to understand the two. It is not like this. It is the slope is different. The slope is 2 times g naught minus g equals, here g equals g naught minus h g naught by r, right? So now it is h by r g naught. Okay, so g naught ends up in the bottom. Okay, so it's a slightly different relationship. You should take a look at this equation in greater detail. So how do they derive this? Maybe this is not correct. I feel this is not correct. So it should also have g naught in the numerator. Okay, so it is 2h by r times g naught only. So it is twice it goes down at twice the rate. Okay, so and therefore you should end up with this equation. This is g naught, right? G naught times 1 minus 2h by r as you go up from the Earth to a height h from the Earth. Okay, so that is merely found by employing the binomial expansion of this 1 by r plus h the whole square. You can write that as, you can take the r square out, so you can write it by 1 by 1 plus h by r the whole square, that is 1 minus 2h by r, right? 1 by 1 plus x equals 1 minus 2x. Okay, so that's they employ that binomial approximation or binomial expansion. Okay, it's not an exact result, it is a rough result. Okay, so Now, variation of the value of g above the Earth. The previous formula explains that g, or acceleration due to gravity, right? We know F equals mg. G is what is that? 9.8, right? Now, if you go a short distance above, it is going to come down, right? And it's going to come down at a certain rate. That rate is 1 minus g naught times 1 minus 2 h by r. As you go a little higher and higher, it goes down at a slightly linear rate, but in reality, the real rate is r square by r square. This one. Okay. So that is the real one, but sometimes you'll be a linear approximator square. This is what you will end up with. Okay. So g is maximum at the surface, as we explained already, right? So now we already discussed this path independence, right? Force acts on a particle, and the particle moves. That is the work done, right? Now we say that in a conservative field, right, and the Earth's gravitation is a conservative field, what happens is that there is a certain path independence. It is only the starting point and the ending point that matter. The path that you take does not matter. Okay, so normally when things go around in a circle, if you leave out the Earth's force, there is no other force. It just keeps going round and round and round and round and round forever. The Earth is 4 billion years old and has been going around the sun forever. Right? The universe is, I think, is several more billion years old. So the total work that is done when this happens is zero. So it keeps happening all the time. Okay. So now we already discussed this dV by dr is the force, the gradient of the potential energy is the force, right? And the total energy, which is half mv squared plus the potential energy, stays constant. Okay, the kinetic energy plus the potential energy is a constant, right? This is very similar to electrical force. Gravitation and electricity are very, very similar. The only difference is that electricity is a much stronger force as compared to gravitation. The electron packs a punch with its little charge and small size far more than the punch that is provided by gravity. Okay. Now, from looking at the two force equations, you can see the similarities in how gravitation force can be considered parallel to the forces between two charges. It's a similar idea, but it's different, right? They also both travel at the speed of light. Okay? So now when you look at f dot dx, I already discussed this. V of x is f dot dx is V is gravitational potential, which is the work done per unit mass. So if you had you add a 1 by m to that, and you do integration from infinity to a particular point x, right? So what is the work done to bring a unit mass from infinity to a particular point? That is defined to be the gravitational potential. So it is 1 by m integral from infinity to x f dot dx. F is gmm by x square. So gmm by x square dx. So you end up with minus gm by x. The m drops out because it cancels. For this, we are discussing gravitational potential, which is per unit mass, right? This is no different from electrostatic potential when if you look at it. Okay. So V infinity, we set it to be equal to 0 or some constant, right? It is and therefore Vx equals negative gm by r. V infinity is set to 0, then you end up with that equation. Now there is what is called conservation of total energy in a gravitational field, right? We already know this. We already discussed this in the context of kinematics, right? After we did kinematics, we then looked at mgh plus half mv square equals constant. Mgh plus half mv square equals constant when there is no when there's no friction or other conserving forces, right? Now, when a body is in a conservative field, there's no external force which is doing work on the body, its total energy is conserved. T plus K equals constant. Therefore, if it is at a distance r and has a velocity, right, the total energy is half mv square plus g mm by r. So it has a starting energy. So you put the a satellite in orbit. You use all the you go to Sriharikota, launch a satellite, and then it ends up in space, right? And then it goes round and round forever, giving you pictures of what's going on down at Earth, right? When I was young, there was a certain Mr. Sharma who became the first Indian to go to space, and when he went to space, um, he had a conversation with the Prime Minister at the time, Mrs. Gandhi. Mrs. Gandhi asked him, "So how does it look from? How does India look from up there? How does India look from space?" And of course, he gave the beautiful answer, which I still remember. And it was, of course, I assume it was a rehearsed question, but still it was a beautiful answer. He said, "Sare jahan se acha." So anyway, so if it moves closer, its kinetic energy goes up, while potential energy correspondingly goes down, right? So now the orbital velocity, right? When a satellite goes to orbit, right? The orbital velocity is what, right? If it has a period t, right, and a radius r, 2 pi r is the distance that it goes in a circle, and t is the period, the time it takes to go, right? So 2 pi r by t is roughly the velocity, right? And so that is given by this formula, square root of mu by a, right? If it is at a distance r and has a velocity v, the total energy half mv square plus gmm by r, right? So now at a height, a total energy is half mv square plus gmm by a, right? And then you can use that to calculate the corresponding value at a different energy, at a different orbit, right? So now, what is escape velocity, right? Let's say there is a body going in the orbit of a particular planet. Okay? Now it wants to leave that orbit and go away, right? Now that the velocity that it should be imparted, right? It is the velocity to be given to a body at its current location, so it leaves the gravitational field and escapes. Okay, so if a body is pushed upwards from the Earth, it can go up and come down, right? So that the total energy is a constant. Now, what is the energy it requires? It requires an energy so that this happens. V infinity equals 0 happens. Okay, so if its total energy is negative gmm by r plus half mv square, then it's got to completely have enough energy to escape, right? So that when does that happen? When you have gmm by r equals half mv square, right? Therefore, we say the escape velocity is square root of 2 gm by r, and this is called the escape velocity to leave the Earth's gravitational field, right? Half mv square equals gm by r will give you the escape velocity, and this is what happens when a body enters the gravitational field of a larger body. Okay. Now, in the case of a satellite, right, what do you end up with, right? You employ gmm by r square plus mv square by r at two different orbits. Okay. So now, right, so using that, you end up with an equation. So if you went up to a height h, right, so you end up with v square equals gm by r plus h. So and v equals r plus h omega, right? So when you use these two equations, you then and then plug in omega equals 2 pi by t, right? You then end up with r plus h equals this formula, right? This is, what does this formula remind you of? Kepler. This is merely t square is proportional to r cube, right? So now at a height h, what will be the period of the satellite, right? Period of the satellite will change. If it is at a higher height, right, than the Earth, then its period will change. So now, at what height is it going to be able to exactly stay on top of wherever it is? Remember, the Earth rotates, right? The Earth rotates about its own axis with a period of 24 hours. So at a certain height, you end up with a set of satellites which follow what is called, which are what are called geostationary. That means if they are over a particular point, they stay over that point. So as the Earth revolves, they are always looking at the same place. So why is that useful? Let's say you spend a lot of money and put one what is that a satellite to understand the what is going on in let us say you are building a satellite to look at what is happening in Tamil Nadu or in Bihar, right? So you put the satellite is always looking at what's happening in Bihar, okay? Otherwise, let's say you are a military satellite, right? Military satellite, you're trying to see what's going on in Kashmir, right? So you put a satellite directly over Kashmir. It is all the time focused on Kashmir. You don't want it to wander away, right? So just then, I was watching one movie called Parmanu, right? Parmanu, there is one satellite that is observing some of these people, and suddenly something comes in the middle. They turn the satellite, look at something else. Meanwhile, something else happens. You know, so the aim of geostationarity is to always be able to look directly above a particular point on the Earth. Okay, so what do you do for that? You have to, the period of the satellite has to be 24 hours. Such a satellite is called geostationary satellite, right? So now what is Ke? Ke is equal to half mv square. Total energy is Ce plus Ke. The mass of a spaceship is 1000 kg. It is to be launched from the Earth's surface into free space. The value of G and R is 10 meters per second and 6400. Right? The required energy for this work will be, what is the energy for work? Gmm by R is the gravitational potential energy, right? And we know G is 10. 10 is Gm by R square, right? And therefore now Gm by R square equals 10. Therefore Gm by R equals R times G. So R is what? 6400. G is 10. So 6400 times 10, right? So, you know, so, so now, what is the, you know, when you do all the calculations needed, M times R times G, right, will give you Gmm by R, right? So you already found Gm by R. So now you need Gmm by R. So now you have to multiply another M. So M times R times G will give you the gravitational potential energy, which is the required energy for this work, right? So that is 1000 times 6400 times 1000 times 10, right? So so that should, if you get all the answers correct, if you do all the multiplication correctly, you'll have 6.4 in the power of 10 joules. All right. So this is a JE problem. A satellite is moving with a constant speed v in a circular orbit about the Earth. An object of mass m is ejected from the satellite such that it just escapes from the gravitational pull of the Earth. The point of its injection the kinetic energy of the object is, right? Gm by r square equals mv square by r. Gm by r equals mv square. One r cancels with the r in the bottom. Therefore, it is mv square. Okay. So the gravitational potential is Gm by r. Therefore, it will be nearly mv square. Very simple problem actually, but if you get it, if you miss the basic idea, then you will get it wrong. Okay, so the k equals minus u at that when you escape from the Earth's gravitational energy, you give enough energy to the body to escape. All right. So all right. So now, acceleration due to gravity problems. The height at which the acceleration due to gravity becomes g by 9, right? Where g is the acceleration due to gravity of surface of the Earth, the radius of the Earth is what, right? So g gm by r square equals g, little g, right? So now at a height h, you have g r square by r square, and that's what they're asking you to find out. Okay, g r square by r square. Now, if you use the other formula, which is the linear one, it will be wrong. That is only for short distances where you can use the linear formula. At big distances, you cannot use linear. You have to use the inverse square law. G times r square by r square. That's what they are asking you to evaluate. So with that, I have gone a few minutes extra today, more than the 1 hour. I am going to stop here. I will come back to discuss gravitation next week. I will continue a little more gravitation, but then we are getting ready to move on to the next set of topics after we complete gravitation. With that, I am going to stop presenting, and we will meet again next week. Actually, we will meet again tomorrow. I will try to continue with the class 12 material. We are continuing with Kirchhoff's laws and with solve problems which involve resistive circuits, and also look at a little bit power related to resistive circuits in this context tomorrow. All right, I'll see you again tomorrow.